Of Pathcast. Today is July 29th, and it's another Tuesday. I'm Rifat Mannan in California, and we are very delighted today to have with us Dr. Hooman Rashidi, who needs no introduction to the pathology world, and he's a very renowned pathologist. And right now, he is at the University of Pittsburgh Medical School, and where he serves many positions. As you can see here, that he serves as the Associate Dean of AI in Medicine, and he is also the professor and endowed chair of Lombardi Shinozuka Experimental Pathology Research. And he also serves as the executive director of CPACE, that is Computational Pathology and AI Center of Excellence. And we are very delighted to have Dr. Rashidi join us today for this lecture. And in fact, this is the 9th lecture in our AI or digital pathology lecture series. And today he is going to talk on reshaping the future of medical care, education, and research, the role of synthetic data, generative AI, and auto-MLs. So over to you, Dr. Rashidi. Thanks for joining us today.
Thank you so much. I appreciate the invite, and I hope you all enjoyed this. Let me turn off my video and minimize this and get going. So again, thanks again for the invite. I do have a few disclosures before I move on. So since some of the stuff that I'm going to be showing you are going to be related to Milo, Sting, PITGPT+, Nebulan GPT, and also our educational series on my role with modern pathology. So without further ado, let me walk you through what the talk outline will entail. Just to make sure we're all on the same page, we'll start off with what is synthetic data and where exactly does generative AI like ChatGPTs of the world and PitGPT Plus and others fall into this synthetic data world. And then also we're going to talk about other types of synthetic data, specifically synthetic tabular data, stuff that you've been familiar with for decades, and also things that you may not be as familiar with that are coming down the pipeline. And then finally, the frameworks such as Sting that actually is enabling the expediting efforts within this synthetic tabular data landscape and how we can actually expedite research by enabling these automated frameworks. So as you all know, everything in AI and machine learning starts with the data. The synthetic data plays a major role within this and for various needs. And if you're wondering how I typically think about data, I usually like to group them into three main groups: real data, synthetic data, and a combination of which. But for the sake of this talk, we're going to concentrate on synthetic data and its benefits and challenges, although we may see some combinations as well. So the story that I'm going to be telling you today really is going to be around different types of synthetic data. So then this way we're all on the same page. So that includes things like generative AI, like things like PitGPT Plus or image makers, that sort of stuff. Tabular synthetic data forms like partially synthetic, like imputations within your databases, and then fully synthetic, data forms as well too. But although all of these have some similarities, they are also distinct entities with marked differences. I think that's the key thing that I want to leave here with during this talk, which is that there's lots of similarities here, but it's very important for the users in the audience to know that, they cannot be all treated as one thing. When we're talking about synthetic data, we typically are referring to it as new data. So this is artificially or synthetically generated new data. The reason this is important is because this new data can mimic the properties of the real data. It's great for using for training and testing ML models, especially when there's a paucity in data. And the other thing is that it could be also sensitive data or costly to obtain data this could also help with. Now, why should you care? The Gartner report has now put out a couple of similar trends, and the theme is basically the same. They're predicting by 2030 that about 2/3 of the data that's going to be used in pretty much all industries, including healthcare, are going to be synthetic and only about 1/3 real data. So this is why it's important for us to care about this realm and be a part of it rather than passive participants. So the types of examples of common synthetic data that are in use, some are things that have enamored the world, like ChatGPTs of the world. These are things like text or things that create images. And so that's things like ChatGPT can create, or Dolly used to, and then Flux and other things. And then synthetic tabular data, which I'll show you more later on in the talk. And so again, the text data could be things like ChatGPT or our own version at Pitt, which is PittGPT Plus, or image generation, as we've built different types of synthetic images here, which I'll show you more later on, or tabular, like EMR type data that could be synthetically generated. But all of this has become made possible through the advances in deep learning, specifically deep neural networks. And so that's what revolutionized the approach to synthetic data generation. And so it's very important for us to credit those who've actually enabled these processes, especially Jeff Hinton and his colleagues, who recently received the Nobel Prize for their groundworking work within deep learning platforms. So how do you generate synthetic image data? Let's start with that. Typically, the neural networks that we use for synthetic image data includes three big ones: the generative adversarial networks, or GANs, diffusion models, and transformer-based models. Here's an example of an acute leukemia that was generated on a diffusion model within our AI center. Another example of synthetic data in practice that could be used for generating or teaching machine learning models of how to get better when they're mixed in with real data is, for example, these. This is, the top left is a real image of a colon cancer. And the follow-up images that are there are synthetic versions that these are synthetic recuts. So if you notice, there's different mitoses levels, different cuts in the glands, different amount of lymphocytic infiltration. And by the way, we've shown this now to a large number of boarded pathologists, and they won't be able to tell the difference between which one was the synthetic, which one's real. Again, stuff like this could be very helpful when there's a paucity of data, or if you want to strengthen the machine learning model's capabilities when the data might be hard to get or scarce. But within that world, we've learned a lot of this synthetic image generations from our radiology colleagues. They've been ahead of the game, and so we were trying to replicate some of the work that they had done within radiology space. And we've seen similar findings within this study, which was that if we build synthetic radiology images, just like pathology, you can now combine them with real images, and that fake and real image concurrently mixed in together, the machine learning models that are built with that bigger data set can give you more generalizable models when tested on held out, tertiary test sets on real data later on. So that was a little glimpse of synthetic image data. What about synthetic text data? These are typically foundation models trained on a broad range of data that usually text data that are also transformer based, so a special type of a neural network. And so these large language models that are transformer based, they're meant to be very good at generating text, especially. And so obviously the one that enamored the whole world was ChatGPT, as you all recall from a couple of years ago. But now we have various custom versions of these and various other companies that have come up with similar setups, some being open source and some closed source. And so here's an example of an open source version that we've built with this PittGPT Plus, which I'll show you how it works later on in this talk. So how do you generate tabular synthetic data? So we talked about image, text, and what about tabular? Tabular synthetic data could also use, both neural network and non-neural network approaches, and at the end can give rise to a synthetically generated, EMR data set, as I'm showing you here. So text and image generators and tabular synthetic data generators, they have lots of similarities, but, especially deep learning platforms that are used to make them, but they also have major differences. And The major differences is because of their intrinsic or maybe end result machine learning models that are built from the data itself, which we'll go through with the talk. So let's start off with generative AI LLMs, since that's probably the most popular thing that everybody wants to tap into. So these are usually involving unstructured data, typically text, but some of the multimodals are now doing text and images. So common examples of a generative AI LLM chatbot, and let's say uses text, for example, is ChatGPT, Claude, Gemini, or even open source ones like Llama, Mistral, etc. And exactly how this works, they're not really doing magic here. These are things that we're, at least foundationally, they're based on things we were used to for decades. And that's on the left side, the traditional machine learning. So as you know, the traditional machine learning before the chat GPTs of the world were things like supervised learning, like where we do classification and regression, where you can tell a difference between cancer or no cancer, or if something's high grade, intermediate grade, or low grade, so on and so forth. What's the difference in the large language models is that they've basically made use of collectively combining the capabilities of all three of the ones on the left. So the unsupervised part basically is where the large language model, deep learning platform basically is let loose into the internet world, and it learns the entire internet by itself. So basically it learns the language. And then you do supervised learning where you tune it to answer the questions the way you want it to answer and get it to answer appropriately and stop appropriately when needed. And then finally, you further fine tune it with reinforcement learning with human feedback, and now even reinforcement learning with AI, where then the final answer becomes very much not only fine tuned to what you're looking for, but also very accurate. So that's what we're going to be concentrating on for the next few minutes on the generative AI and exactly how that actually works. So as I mentioned to you here as a repeat of what I was saying, it's a combination of unsupervised, supervised, and reinforcement learning. So you really start off with unsupervised learning, followed by tuning it with a supervised instruct approach with your prompts and completions, where then that base model then learns better. And then finally, you do reinforcement learning with human feedback or with AI that align the final response to more what the human expects. So exactly what is under the hood of these things? I think it's best if I show it to you in this quick video. As I was just mentioning, you start off with the pre-training, where it's the unsupervised pre-training, where you now learn the internet, let's say. And then afterwards, you do supervised instruct step, where if you notice from the blue and in the orange, you improved the response accuracy in terms of what the human was expecting. And then finally, you further align it with the final response that the human is looking for with the reinforcement learning with human feedback. Now, exactly what's happening under the hood itself. So as you type in your information, let's say what molecule carries oxygen, for example. And so you know it's hemoglobin. But now what happens is the machine breaks down those words into what we call tokens. And then those tokens are then assigned specific numerical vector arrays, we call them. Now, for simplicity's sake, I didn't show the actual tokens, just the actual words. But just the concept is similar, where now those numerical values are then fed into those layers of the transformer, and then probabilistically gives you the most likely next response or next word that should pop up. And then as you expect, then you get the final output. In this case here, it says it was hemoglobin. But if you notice, that also gave a whole paragraph on top of the hemoglobin answer. So the advantage of this is you obviously have an explanation now associated with the hemoglobin, and that's great. But the disadvantage is, as opposed to a typical classification where you now could have stopped and kept it simple in terms of the response, here now you have to also deal with what happens if the paragraph has context errors. What if the tiniest word changed the entire meaning of the entire paragraph? So these are things that we have to think about as we tackle and wanting to bring on these very powerful platforms into our practices. So this was a text-based LLM tool that has revolutionized natural language processing. But you may ask, what are some of the other limitations that we're talking about? So obviously, one of the biggest limitations is these are typically general large language models. And so they're not very good at very specific disciplines, especially very specialized medical disciplines. So that's one big issue. The second thing is their API costs could actually make it cost prohibitive for certain tasks, especially if the number of users increase. And then finally, the ones that a lot of people are very concerned about is around IP transparency and also data security. Is the data secure as it's going up to the cloud into these frameworks? And should you be using this for various types of questions and not? So how do you overcome these data security and cost limitations? So one way around that is you could use on-prem local LLM chatbots with open source frameworks. So an example is like the one that we have here. And pretty soon in the next month or so, you should be able to, get this on your own platform. We're making it fully open source for the global community. And it's called Nebulin GPT. Basically, it's your chat GPT that's running locally on your regular laptop or on your computer with no internet needed. And so exactly how does this look? So here's a very similar look to the chat GPTs or other types of LLM GUIs. So you basically can see that there is no Wi-Fi connection there. In the top left, it was my Wi-Fi and there was no Wi-Fi. And then you can now ask it questions in a nice table format, compare and contrast PCA, TSNE, and UMOP with examples in medicine. And again, with no Wi-Fi, this is able to spit out a similar answer to what ChatGPT gives you, but again, all fully private. So very nice, cohesive responses in a nice table format, but 100% private. So here's an example of an open source framework that could give you similar results. But these things that I'm talking about, like the ChatGPTs or Nebulin GPT that I just showed you, are still general chatbots. They're not specific for our given medical specialty domains. So how do you overcome nearly all the other limitations that I had listed? So, and the way to do that is you customize those while keeping them local. So what do I mean by this? The way we customize LLMs, there are really three major ways. Pre-training is one way, which is not an option for most of us since this is really reserved for the bigger companies, the OpenAI, Microsoft's, Google's, where they have tens of millions of dollars to be able to spend on training these things from scratch. But we can do sometimes those things, but they're not the common ground. The ones that we could tackle much easier would be fine-tuning the large language model, especially if they're open source, like a Llama 3, for example, or doing RAG model where we can talk to in context with your own specific data set of interest, where RAG or retrieval augmented generation can do that for you. Whereas the name implies, you're augmenting the retrieval and the generation based on a very specific data set that you're tapping into. Now, in combination of those could even be better. Fine-tuning model and doing RAG on top of that, and you become very specialized and you can get very accurate response from there. And so our solution around that was our PittGPT Plus, which is our local custom LLM framework, which does multiple things. And one is, you noticed in this video, there is no Wi-Fi connection again, just like the Nebulin GPT. And what we're doing is we're going to be talking to not a general chatbot, we're going to be building a very specific chatbot. So specific for, let's say, my own domain where I practice. I'm a hematopathologist. So for leukemia, lymphoma, diagnostic criteria from WHO and ICC and others, I would want to build a chatbot that can actually be able to answer my questions appropriately. So how do I do that? So I can, just like any framework as you're building from scratch, we're going to do some negative and positive control. I'm going to first upload my data sets. And so here's all my heme documents, my papers that I wanted to talk to. So, Dan Arbor's blood paper and others. And then you can also see exactly what you brought in. It's a clump of different documents that have very similar, information around heme. So now I'm going to do a negative control test. Since I'm a big soccer fan, I'm going to say, who are the best soccer players in the world? And this would be my negative control. Since there is no documents around soccer, this machine should not be able to answer the question around soccer. And you can see that it's also very transparent in terms of what's happening where in this whole process. And right now it's handed off the final response assessment to the final large language model, and it gives you an answer and says, I don't know since the query is outside of my knowledge base. So, and that's great because we didn't know how to have soccer in those documents. But it's also smart enough to know that these were all hematologic, entities that were in the documents that it looked at. So I can clear this, and now I can do my positive control since I'm building a new platform, a new testing platform. And so for this new positive control, I now added the document that has the soccer players in there. And you can see right there, it's a distinct entity away from the clump of the heme documents. And so now if I ask it the question of who are the best soccer players in the world, this now is going to dig in, and now it's going to pull the information from that document that I've now uploaded. And that document says the best soccer players are Messi, Ronaldo, Salah, Mbappe, and let's not forget Hooman Rashidi. And again, you can see that it's, joking aside, it's very in tune with what I had fed it in. And so you can also see where it got the information from. So now that you've done your positive and negative control, you can now ask it questions, let's say around heme path. So I'm going to ask it a question about somebody who should have CML chronic phase. So this patient has an elevated platelets, 4% blast, BCR-ABL positive. So this should be a CML chronic phase. And as you expect, this thing had dug into those literatures and basically found which criteria causes for what. And based on those, it gives me the final good answer around BCR-ABL, and you can see exactly where that information from the paper was dug out of. And daily I deal with headaches around ICC and WHO criteria, which most of us in HemePath deal with. And so if I ask it, questions around that, it could answer that too. But in this case here, it has memory too for that question. If I upped it to 17% blast for that CML case and said if that blast count was above 17%, what would be the answer? It now says, well, now the 17% is between 10 and 19%. And based on criteria, that makes it an accelerated phase, as you can see in the bottom. And so it got the correct answer as expected. But again, you can see where you got that information from. So it didn't make it up, and it did it based on the papers that you had fed in. And I was telling you right now about the ICC and WHO criteria. Well, what if I wanted to make a nice table for me that finds them 9 major differences between WHO and ICC criteria? Well, this now digs in there, finds that the differences, and gives me the nice table around those 9 differences. But it's also smart enough to know that there are more than 9 differences between those 2 criterias. And so at the bottom, besides giving the classic differences like elimination of EB2 in the ICC and so on and so forth, it basically says the additional ones besides those 9 are the other 3 that was listed. And again, shows you where that was taken from. So brings user trust into the mix, and you can verify the information before you actually want to act on it. So this was, and I can go on for a long time on this because it's got other bells and whistles, but this was PITGPT Plus in a nutshell. Basically, super fast way for anyone with no code to be able to build their own subspecialty custom chatbots. The benefits of this PGPT Plus that we have is the reduced hallucination, so it's more accurate, or confabulation, some people like to call it. Cost effectiveness, it reduces reliance on expensive API costs, more scalable. It got enhanced controls in terms of fine-tuning for specific subspecialties, so better data governance. And then the one that a lot of people care about just as much as data security, since you can run these locally, you don't need to actually have it on a cloud. So you can run on your own laptop as I was doing it, as you had seen. So regardless of the LLM solution, generative AI reproducibility has its own unique set of issues. The LLM output performances follow things like perplexity score, blue score, rouge score, or maybe you may want to use another LLM to assess the other LLM's output. Long story short, none of these are perfect, and none of them are considered gold standard. The gold standard is still currently seen as the human expert assessment. And so we don't have that yet in terms of an automated framework. It's still human expert making the call as they go through the process. But I'm sure with time, we'll be able to automate this. It's just that it's a lot more challenging within subspecialty fields where the number of users may not be as many to actually make those assessments and automate the such. So The LLMs, as you can see, their final assessment is not as straightforward as like your classic supervised learning platforms like regression and classification, especially classifications like has classic confusion matrix-based measures where most people are familiar with things like accuracy, sensitivity, specificity, versus in LLMs, the perplexity, BLUE score, and whatnot, most end users are not that familiar with them. So that's something to keep in mind as you dug into the space. So that was generative AI through LLMs. What about non-LLM generation of tabular synthetic data? This is stuff that a lot of us have, done. So I'm sure in the audience right now, many of you have done studies that use tabular data, and you have included synthetic versions in them, meaning that you probably imputed some missing values maybe in there. These are typically, when we say tabular data, we're talking about structured data. And so this is like your typical Excel file with a bunch of numbers, so that there are numerical values and some target, and then they're all structured within an Excel type file, like let's say CSV file. And then the end result of what you build from these are things like typically like, a regression or classifications. And then their reliability measures like correlations, QQ plot accuracy, ROCs are much more better well known to the end users as well. The types of synthetic data generation for tabular numerical data, there are really two big versions there. One is partially synthetic, as I was mentioning. So this is things like a mix of real and synthetic that we've been doing for decades. And this is what I mean by partially synthetic, is where you've imputed the missing values. So let's say you have, a few thousand numerical values in your data set and certain boxes are empty. And then those boxes that are empty, let's say under blood pressure, may get refilled with some imputed value, some inferred value. So that's the synthetic value that you've inferred in there. But the other possibility is, instead of having partially synthetic, you can have all synthetic, where the entire thing is synthetic and made up. And there is no real information, so no real patient information left anymore. So are these tools can they be automated, these partially synthetic data generations, or even fully synthetic? And so I'm going to start off with the partially synthetic ones and how they can actually be, expedited. If you have, let's say, a typical real data set and you now have missing values in it, can you clean up that data set in a much faster way than possible? And the answer is absolutely. Nowadays, you could use our Milo's open source automated pre-processing tool. So this is something you can download and start using right away, as I'll show you in a second. And it can basically clean up your entire data set that would have taken you usually days to maybe weeks within minutes to less than an hour. And so here's an example of something that you could basically do. This is a fake data set that I'm bringing in just to prove the point. And so this data set has a bunch of missing values. It has a couple of targets that are not numerical values, a target like your breast cancer target that says positive and negative, and a risk target that has high, intermediate, and low. And so exactly how can you clean up that data set within Milo's app tool? And so the Milo's app tool is very simple. You click it, and again, it's all on-prem. So your stuff is fully private on your own laptop or whatever that you're using internally. And you upload the data set that I just showed you. So this one had 697 rows of patients, 11 columns, and 3% missing values. And then you follow the simple 7-step human-in-the-loop process throughout the cleaning process. So I'm going to pick the target being cancer that I want to build the machine learning model on later on. And so then I'm going to follow that 7-step process as I follow through. So the second step, you do a basic univariate analysis of what was brought in, or tabular data sets, and everything looks fine. And then the third step, you do a quick little bookkeeping, and everything looks fine, and it shows you where the missing values are mainly concentrated about the positive and negative class. It automatically knows that negative is a 0 and a positive is a 1, but you could change that based on your needs. Maybe positive for you might have been a 0 for what you're trying to build. But most of the time, that's what it is, though. And then finally, in the fourth step, it basically also can do column assessments. So it can figure out which columns for example, are giving rise to the missing values. So in this case here, the bare nucleoli column was giving rise to almost half of the missing values. So for the sake of this case, I'm going to remove the bare nucleoli, and you notice now the missing data goes from 24 to 10. And so I'm going to be imputing much lower numbers now. I feel much better about that. And then in the fifth step, you had that column, the risk column, that was also text. And the machine knows that, okay, here's the text the machine won't understand. Let me convert it to numerical values. So it will remove the risk column, create 3 separate binary column, what we call one-hot encoding. You can also remove the column if you don't want to do that. And then by doing that, you now made it all numerical. And then finally, most people bring in a single data set that they're trying to build machine learning models on. So then you would have to heuristically build 2 separate data sets out of that initial data set. As you can see right here, those orange bars are the missing values. If I click impute, you now are going to impute those positive and negative oranges just in the training and initial validation part. And I'm going to make it 150 each just to kind of prepare it for my machine learning run. That way, the generalization test set has no synthetic data in it. So then the final response, final model's performance is be as realistic as possible. So you're following machine learning imputation best practices as well. And then finally, you can also do multicollinearity assessment just to see if there is, certain columns that may be having too much correlation with each other that could cause problems. So in this case here, shape uniformity and size uniformity columns have an R value of 0.91. So I can remove one of them so has less of an issue of overlapping or having too much of the same thing being present. And so by clicking in and removing it, I can say next. And from here, you now can finalize that final document. So you started with a single tabular data set. You now went to 2 of them. So it's ready for your machine learning study to be started. How many columns you removed, how many you've added are all listed. And it shows you exactly what the new machine learning files are called. Training, initial validation, and generalization testing, which you can just put into Milo's Auto-ML and build your model within 5 minutes. And so you can also see the audit files after when you get the full zip file opened up. And then you can see exactly what was brought in. So these were the training, initial validation. And you can see now there are no missing values, no text values. And the thing is completely clean and ready to actually be starting your machine learning study on. So, and there's a lot more that I can talk about around Milo, but I'll defer that to you guys as you want to play with it, when you download it on your own thing and just see how it fits your own needs. So that was a quick reminder of partial synthetic data and how we are using machine learning to expedite its cleaning that's actually present within real data sets. But since that's a real data set that you're now adding tabular data into, not surprisingly, as it should be under a full regulatory umbrella of real data because it's basically real data. And not, and we typically know those could take weeks to months to get IRB approval on, and in terms of to do the actual study. So if you had a brilliant idea and you wanted to now test out your idea, you really would have to first get, there is no playground for you to be able to jump into and test out your idea for any idea that you may have in your mind. But what if you needed that data right away to test out your idea immediately? Well, in order to do that, you would really can't touch the real data, so you would have to think of alternatives. And the alternative would be an all-synthetic tabular data. So what exactly are an all-synthetic tabular data? So this is definitely not the same thing as de-identified real data, because de-identified real data can, theoretically be re-identified, and all synthetic tabular data, the likelihood of you being able to match it to any real patient, because it's not based on any real patients, at the end when it's basically produced, it's very close to 0. And so this is new data that you've generated now. So it's not de-identified real data. It's brand spanking new data. So the rows are basically fake rows of patients, but then collectively those rows match the collective, performance and profiles of the real data that it was used to make those. So they can emulate the real data counterparts because they've maintained the mathematical relationships of the real data that it represents as its function. especially useful for pilot studies. And by no means I'm inferring or suggesting that this using an all synthetic tabular data is a way of replacing real data usage. This is just as an added tool in our arsenal of research that you would want to do to expedite more studies, more quality, more other types of research studies, so the ideas don't die off. So it's just a complement to our pre-existing real data. So the ideas can actually be further nourished. And then when there is a need to get additional real data, when you're probably on the right path, then you get the real data and dive in further. So fully synthetic data in action, these are, a lot of different groups have done this types of work. So I'm going to show you one of our works which was basically, we were trying to verify another group's work with now testing it on our synthetic data machine learning models on specifically active tuberculosis cases. And this was with our collaborators in Pakistan and also the leadership of Amazon, who brought in their synthetic data generation arm to help us out. And we used Milo Auto-ML to be able to build the models that actually can predict the stuff. A long story short, what we found was similar to the other groups, that the real data performances can be matched very closely with the training on synthetic versions as well, especially if you expand the synthetic data set. So in summary, this and other similar studies, support the utility of using all synthetic data, especially for pilot studies. But that study that I just showed you took a bunch of back and forths and was about 4 months to complete. So the big question I always had was, can this process be fully automated, or at least, almost fully automated? And also the quality of the synthetic data, can that be enhanced compared to the one that we've ran or even others have run? But then in order for you to do that and automate the process, how do you best, actually get the best all synthetic tabular data? In order for somebody to be able to automate this process and get the best all synthetic tabular data, you have to have an unbiased tabular synthetic data generation process. So the neural network that's actually making those has to be as unbiased as possible. And most importantly, you can't base the final synthetic data's correlation to the real data based on your basic statistical measures, because you may be off. And so in order to truly show how the synthetic data actually would perform, you would have to take your synthetic data, build machine learning models on those, and then not only test it on synthetic test sets, but more importantly, on held out real test sets to see if it would actually work if you brought in real test sets into it to test it out. And so having an embedded Auto-ML, automated machine learning validation, built into this framework would be just as important. So that way you assure data privacy and better representation of the real data. So our solution to this was Sting, and Sting was able to do all of this for us. So Sting stands for Synthetic Tabular Neural Generator. Now, exactly, let's say you have, current challenges that you're dealing with, and you want to overcome these, and this is with HIPAA or maybe sensitive information that you may want to share with another institution or an industry partner. And of course, there's lots of challenges for us to overcome when we're dealing with real data. And so a solution around that would be especially for certain subset of pilot studies, would be using synthetic data instead of the real data to test out the idea first, maybe. And so the big question that people usually ask when I bring this up is, how do you know if the synthetic data performs just as well as the real data? And I was mentioning to you is, if you have a framework like within what we have in Sting that automatically builds machine learning models for you on the synthetically generated data sets, and then more importantly, tests it with real data on its secondary, tertiary, quaternary data sets, then if you show that they actually perform well, then that you have basically a validated synthetic data set. If they don't, you don't have a synthetic data set that's validated. So our solution was, within Sting, we wanted to use the real data in the background as basically the ground truth positive control. And that ground truth then would stay on the side, and then you would use the synthetic data that basically gets generated from a subset of the real data. to then build machine learning models on. And then those machine learning models get tested with synthetic test sets. And then in order for you to say that those are actually working or not, is you now can't stop there and you have to test it on real test sets now. And so if it performs well on real test sets, then and does well, then you're on the right track. And so how does Sting actually do this? In this diagram, it nicely covers it. So let's say somebody comes in and says, give me 1,000 cases of patients and asks their honest broker or IT personnel and says, I want at least 300 confirmed sepsis patients and 700 no sepsis patients. So in the first arm of Sting, which is the green part that you'll see here, that's the control arm, that those 1,000 cases are being automatically split up and you're building your machine learning models on. So you'll know what the ground truth would be with two separate test sets. So let's say it came out to 89 ROC, you kind of know where you're at in terms of your baseline. Then what happens in this purple box is a subset of the real data is used with the deep learning platforms to actually generate the synthetic data sets. And then those synthetic data sets go through the same thing we did in the green. They now also get split up and you build machine learning models around that. And you then see how well they're actually performing on their primary and secondary synthetic test sets. But then in order to show that how well they're actually doing, you then also test it on that dotted green line with the real held out test set as well. And if you actually do well in all three of those test sets, then you become the blue validated synthetic data set. If you don't do well, you're the red, you're not validated. And the reason there is an IP around this with Cleveland Clinic is because we made a no assumption approach, plus we have our four unique versions of our own synthetic data generation arm. And by having 8 different synthetic data generators basically running simultaneously, you're increasing the likelihood of more of the blue validated synthetic data sets. Basically, it's basically like a gladiator space where a bunch of folks are fighting for who's going to win over as being the best synthetic data generator that's validated. And the one that wins over, might be more than one, then basically becomes your 1 or 2 or 3 validated synthetic data sets. And this video shows basically exactly what I'm talking about, much better. So let's say your IT personnel gets a request and somebody says, I want to test out and build heart disease cases. They pull the heart disease real cases and they put it inside Sting. And again, it's fully on-prem, so there's nothing that's going in the cloud. And then the prior data sets that were run, like pancreatic cancer, diabetes, and breast cancer are there. So now you pull up the heart disease case. So if they can attach a file into an email, they can work with Sting. It's that simple. And then the investigator had specifically initially had asked that they cared about heart disease prediction. So again, the investigator doesn't see any of this stuff. It's just the IT personnel, the honest broker that's running these. And then it pulls in the few hundred cases that it found. You can do a quick little quality check in terms of seeing what was brought in. And so after they've done their quick little quality check, they now say, okay, let's start the job. And once they start the job, the same stuff that I showed you in that green and purple diagram is happening here now within the software live. So that orange or the yellow one is the real data set that's creating the real machine learning model control arm. And then the 8 that I showed the box around that's underneath it, the gray stuff, those are the 8 separate synthetic data generation arms. And so now you know that the real data, if you had trained machine learning models on, would have had an ROC of 86. And then you now wait for the other 8 synthetic data generators to follow suit. And the blue is the secondary synthetic test set, and the green is the tertiary held out real test set. So then you can also compare them side by side to how well they did. So this one here showed the real one had a multi-layer perceptron that actually performed really well, and for this particular study, and so that is your ground truth. And then you can see also visually that the one in the middle, Gaussian copula, seems to be the best one. It also has a similar Sting ML score, so mathematically it also matches. So that seems to be the best model that popped up, and raised up to the top. You can then click that model and see how well the real and the synthetics match. And you can also expand the data set instead of just a 1-to-1. You could make it 1-to-5. So that 300 cases could be 1,500 cases. You can also run Auto-MLs on those to see how well they do and kind of download them. But more importantly, you can also, with the best practices of comparing synthetic to real data sets, we've kept the standard measures there still as well too. So the non-machine learning measures like COMSUM plot of seeing how the real and the synthetic match, like in terms of the blue and the orange, you notice that they're similar in terms of their COMSUM plots, their distribution plots, and also their QQ plots. They seem to be matching very nicely between the synthetic and the real. And then a lot of people want to see also what the mean and standard deviation globally shows, and it seems like they're very nicely matching too. So here's an example of not only the machine learning model shows you that it's performed really well, also the standard statistical measures also showing you similar stuff. And you can also see how well it actually performs. So the likelihood of you having 3 separate ROC and other performance measures to be nearly identical to each other by chance is very, very small. So this seems like a great example of a validated synthetic tabular data set that Sting has generated. So now your honest broker can click that and download that synthetic data set for you. And now you have heart disease S that now can be given to the investigator for them to actually use with a lot less IRB oversight, hopefully. And so that was Sting in a nutshell. Its unique aspects are the end result is a more realistic and validated synthetic data. It's got 3 separate testing sets working in the background. So the likelihood of you giving something by chance is much lower, and it's all on-prem as from a data security standpoint. It's validated on 12 different data set studies. So 10 binary and 2 multi-class, and I'll let you defer the paper to you for you to read more about that. And how do I envision, this is what I'm going to finish with, of how our Sting can help our current landscape. So the current landscape versus our future proposed Sting landscape. So our current landscape where there is no Sting, somebody will have a brilliant idea, and now they want to go get access to the data. And we all know everybody's super busy. The minute they're thinking about IRB and all sorts of paperwork they will have to do, that huge climb, a lot of people won't pursue that, and these brilliant ideas will die off. And so what happens if you have Sting around? Well, with Sting, you now can actually generate the stuff with a lot less IRB oversight, hopefully, and depends to your institution's IRB regulation and their leniency towards these things. But more importantly, because they're fake data, hopefully they'll be more lenient towards them. And then more importantly, you can get that study and that brilliant idea tested right away to see if it's even worthwhile pursuing. So that is it worthwhile later on getting the IRB for the real stuff later on. And then, but besides that is also around multi-institutional studies. Currently with the No Sting platform, the partners or other institutions or industry partners come to play. They are thinking about all the headaches and all the paperwork they will have to go through. Most of them would not even pursue this. So that would mean, loss of collaboration and even loss of revenue to a lot of institutions. But within the Sting landscape, you now, as you've built out these synthetic data sets, you've now have created synthetic data biobanks. So those synthetic data biobanks could actually be ways where you can help with various digital twin and other frameworks that people are interested in testing, or maybe even, rare disease studies that could need a federated site, so on and so forth. Long story short, the access to the data is expedited and it increases collaborations. So in summary, Sting drastically lowers the bar for access to synthetic data, dramatically expediting pilot study timelines as a complement to your real studies that we'll pursue, encouraging more pilot studies to be done within your institution. So there's more intra and inter-institutional collaborations. And obviously, you can also get your synthetic data biobanks going. So that would be great for your industry partners, institutional partners, regulatory organizations, so on and so forth. Our Sting team, I do want to thank, and they were instrumental of making this happen. So it takes a village to make a lot of the things that I showed you work. So I do also want to thank our PITGPT Plus and CPACE collaborators for other stuff that I showed you. I do want to leave you with our 7-part review article series in modern pathology. For those of you who are interested in AI, this will let you start in that path in a no code, no heavy math, just conceptual workflow as you learn the concepts in Article 1, deeper dive into the generative AI in Article 2, predictive analytics in Article 3, statistics of both generative and non-generative AI, and their similarities and differences, regulatory aspects of them, ethics and bias considerations, and how to overcome or minimize those issues. And then finally, ML ops and future AI with multi-agentic frameworks and others. I thank you for your attention, and I hope you enjoyed it, and happy to take any questions. Thank you so much.
Thank you so much, Dr. Rashidi. That was a great talk covering so many nuances and details about LLMs and synthetic data. That was really engaging and very illuminating. There are quite a few questions that I can see online. So one question is from one of our viewer who is watching from India, who is not a medical professional. So his question is that to set up the local setup, so do you need special hardware or it will work in a Mac Pro M2, M3 processor?
Yeah, that's a great question. I would say if you're talking about, so first off, all the stuff that I showed you would work on, a pretty good laptop even. Now, obviously, it won't be as fast as an HPC or high performance computing, for example. But the ones that I showed you, they were all with basically on a MacBook. So if you have Milo will work just as easily on a MacBook Pro, M2, M3, that would work, no problem. Just go to Milo for Education and download it. Nebulin will have to give you those access later on. We haven't made it public yet, but it will be public soon. The other ones, Sting, I would have to defer you to the Cleveland Clinic folks because they own the IP. I was just the inventor. And PittGPT Plus is Pitt hasn't formally come up with a plan of how to release that. So I hope that gives you a better perspective.
Thank you. Thank you again, Dr. Rashidi. Here's another follow-up question, I think maybe somewhat unrelated. So the question is that garbage in and garbage out, is that a possibility with synthetic data?
Of course, yeah. No, that's a great point. So by no means we're basically, the nice thing about it is that because we have the Auto-MLs built in, if you put in, no good data that would have not given you great results if you built, machine learning models on the real version, synthetic data is not just going to, magically make it better. As a matter of fact, we even published on this concept not on synthetic data, but the concept of garbage in, garbage out is, and if you go into transplantation and look at our delayed graft function study with our transplant colleagues, we were able to show that even though we used Milo's Auto-ML to expedite the study by building 400,000 plus models, that because the delayed graft function studies that have been up to that point shown that they had at most, ROC values of in the low 70s, Milo didn't magically make it 90s. It still stayed in the mid 70s. It did improve it, but it didn't make it something that was not real. So you're 100% right. Garbage in, garbage out. The other thing is within that framework is also the being aware of biases. That's something we have not fine-tuned still yet within these frameworks. So even though these frameworks are very powerful, if you have a bias towards one population that you started with in the real data, the synthetic data may exaggerate that in the final version that it provided you. Although some people argue that the synthetic data could also help that by then concentrating on the underrepresented, let's say, group. But we have not done that part. That needs subtle variations of our frameworks. So yes, these are basically tools that have limitations, and of course needs experts like you guys to kind of dive in and work with them, but also being aware that they should also always be questioned on their output.
Thank you again, Dr. Rashidi. Couple of more questions regarding Sting actually. Can you explain how Sting differs from conventional transformer-based LLMs like GPT-4 in terms of architecture or training paradigm?
Yeah, that's a great question. That I got that question from another conference too. So I have to tell you, because, and I'm guessing two things. One is people have asked me this before. They're like, hey, why do I need Sting if I can go into, something like ChatGPT, like a transformer-based setup, upload my data set, and then ask it to create me a synthetic version in ChatGPT? And you can do that for sure. But the problem is twofold. One, you're not going to get the stuff that Sting is doing. You're not going to get this validation of the machine learning models that are built on the real, knowing how well they would have actually done in real practice, how well the actual synthetic form would have performed on machine learning aspects, how do they compare to each other to the real. So, so the biggest difference is which one are, if you're looking for, kind of like if you're showing kids, let's say that I have an idea, let me show you how easy it is to kind of upload something and create some fake versions. ChatGPT would be an easy way to show somebody that. If you're looking to do it scientifically, I would not do that at all, because the stuff that you're going to get out of ChatGPT, unless you've built a very elaborate framework that also cross-validates, which I have not seen, then it's not going to give you reliable, validated data sets. So that's one. So in terms of the output of the two are very different, Sting and what ChatGPT or Claude or Gemini or whichever that you're using gives you. The second thing is the infrastructure or the architecture of Sting is very different than the ChatGPT. The architecture of Sting, the typical ChatGPT or things like ChatGPT, they're transformer-based neural networks. The Sting framework, the synthetic tabular neural generator arms, there are four major different types of arms. There are generative adversarial network variations, so like CT-GAN and other types of GAN. And then there is a TVAE, which is a tabular variational autoencoder that's used. So it's a different type of a neural network, again, not transformer. And then on top of that, we also have more elaborate statistical non-neural network approaches in there too, like a Gaussian copula approach. And so it's the combination of these different neural networks that are fighting each other versus a typical ChatGPT is a single transformer that's actually doing your stuff, or it might be a mixture of agents as well too. So it could be multiple transformers. But the take-home point is their infrastructure. I mean, architecturally, they're very different from each other. I hope that answered it.
Oh, thank you so much, Dr. Rashidi. Couple of more questions. There is one question about offline uses of, like large language models that you mentioned. So
Yeah.
the one question that has come up from one of our viewers is that how do you address the limitations of offline LLMs in pathology, especially, when you talk about tasks that require frequent data updates like new WHO classification or rare case reporting or things like that?
Yeah, so that's a great point. So that PITGPT Plus that I showed you does exactly that. So with PITGPT Plus, if I have brand new literature that popped up, or let's say there's updates on WHO, I basically quickly upload those into the framework, and my large language model now knows those new documents and will talk to that alone. Now, you're correct that a general chatbot would not have that information unless they're tapping into the internet and looking it up and stuff like that. And I'm not very trustworthy of the general chatbots because they hallucinate or confabulate things not so infrequently. Even the deep research frameworks, they're not perfect. So having a customized way where you can talk to your own documents, so you as the expert have uploaded the stuff, that's, in my opinion, is the best approach moving forward. The other thing is you should be aware of how you use your stuff. And this is something I'm putting my Dean of AI hat on, of what we teach the med students, grad students, and faculty and staff, is we have this very simple mnemonic that we use at Pitt School of Medicine. And I'm copying my friend Jason Rosenstock, who came up with the mnemonic. And this is what we teach our folks, which is our DVP rules. And the DVP rule is very simple. when you're using a generative AI or a large language model to basically let it spit out answers for you, you first have to follow D, meaning that you have to disclose. So D for disclose. And you have to tell people that you've used it so that they know what part of it you used. Same way that you're publishing papers, you tell exactly what the large language model was used for to create your outline or whatever that you've done. So you want to be very honest about what you've done so that there is no question of who's done what. So that's the first thing. So disclose, so D for disclose. V for verify, you have to verify the information. These things have confabulations, errors, slash hallucinations, people used to call them. So you got to be careful that you're not using basically incorrect information, that you're verifying the references, verifying the information. Just because this has spit it out doesn't mean that it's real. So human in the loop the whole time, verification, so V for verify. And then lastly, P for protect. You have to be protecting your data so that you're not putting, sensitive information into the, like HIPAA information into the cloud, or maybe, things that are against the policies of your institution, copyright stuff, whatever that, basically will not be allowable, you have to be protective. So again, disclose, D for disclose, V for verify, and P for protect, DVP. If you follow that, I would say you probably cover yourself 99, maybe 98, 99% of the time.
I think that's a great point that you mentioned, Dr. Rashidi, because most of the time, like there is this question of hallucination that you can see it yourself, like whether it is medicine or not, and it can be so dangerous in medicine, even if when we are using ChatGPT or other LLMs for simple things, you will see that it is hallucinating so much. You have to be really
Exactly.
careful. So
Exactly.
there is a question that nowadays, like many of the bigger institutions and hospitals are coming up with their own LLMs, right? Like, I mean, versions of ChatGPT, so to say. I think you were talking about in PIT also you have a PIT
Yeah.
LLM, right? And I think in our hospital also at City of Hope, they have recently launched a Hope LLM. So
Mhm.
what do you think is, first of all, what is your experience on it? And then what do you think is the actual utility about their integration into, EMRs and how useful they are? And what do you think is the future of local LLMs in hospital settings?
Yeah, I think that's a very, I'll be honest with you, I don't know exactly what's going to happen like in the next couple of years. I, I I think we have a mix of folks in terms of, being receptive to include them or not. I think many people are receptive to wanting to include generative AI frameworks into hospital systems. I just think that we need to be super careful because these LLM frameworks can also do harm. They can, and you won't even realize that they're doing harm. So I'll give you a great example. And we got to be also very careful in terms of who's deploying these things because and some of these folks are some of the biggest minds in the industry, like for example, tools like Office 365. That's a de facto a software tool that everybody's using, right? You kind of like are expected to use Word, PowerPoint, and other things. And so within these, they've now incorporated various Copilot setups and your LLM setups. And it sounds, at first glance, sounds awesome because you just like, oh my God, the LLM is going to help me with all my daily stuff. But I have to tell you, I've also seen the opposite end too. I've seen folks who use the thing and allowed the LLM to take over, and now the LLM is slowing certain parts of their day down because it's changing things that they did not want to change. It pulls in documents in from one Teams meeting to another Teams meeting where it could also be a security issue as well. And so but I'm very optimistic thinking that these are bugs we're dealing with right now. That I think with time and with multiple agentic frameworks that these nuance annoyances and errors, if you will, are going to get worked out, with time. But that being said, I'm very much on the human in the loop camp, especially knowing that these things make mistakes. And there is no machine learning or AI tool that's 100%. That's a fact. And so knowing that we don't have anything that's perfect, how do we make sure that we're constantly, validating and staying on top of things? And I don't have an answer to this, because this is a very challenging thing that we need to kind of stay on top of, because if your LLM tool from a major known entity basically starts showing incredible results to you, and you now see, day in, day out, almost like an, spell checker, where it does the spell check for you, but now it's writing the whole thing too. Just like the spell checker, where we realized that something spell checked something that it shouldn't have, and then all of a sudden it spell checked it to something that was not supposed to be there. And same thing here is we're letting those go because we've become so used to the LLM and the AI tools or the automated frameworks. I just don't know how can we continuously stay with the human in the loop, knowing that human nature will want to kind of take the path of least resistance and not check things. I just think we have to always, have something in the back of our minds that these things can make mistakes and it could actually cause problems. So let's make sure we always read their stuff. And the reason it's so important in our space is because when they make a mistake, making a mistake for making a call on your movie recommendation from, Netflix is one thing, or Amazon, and what thing you're going to be buying is another thing. No harm done, usually. Here, you make a mistake, you now could change somebody's chemotherapy potential or prognostic indicators, or maybe the diagnosis. And so I think it's very important for us as practitioners to be very vigilant as we're using these things and keeping in mind that they have limitations. That's why I hate to kind of like, pull you back into that review article series. I think if you read that review article series, on purpose, we've included these other elements like bias, regulatory elements, statistics, study design, and for you to kind of know the differences between them, because you as the end user are going to be expected to be the one who keeps these things in check in our environments. And one last thing I also want to say, if you're wondering why I'm pitching the education piece, is because I'm convinced that we have a major, paucity, or I should say even void, in terms of AI-enabled practitioners. Right now, and especially like in things like tumor board, for example, you're going to a tumor board, you have representatives from every single subspecialty there who's basically saying, here's the limitations of my surgery because the surgeon said something, or the oncologist says, yeah, the side effects of the chemo also causes this. I'm not sure if we're going to use this. Pathologist says, yeah, there's also another differential in the diagnosis. Radiologist says the same thing. Social worker will say, well, you have to think about maybe the patient won't take XYZ. So all the people who are involved, they all know about their advantages and limitations of their own world as they bring on this cohesive decision that's going to enable the best care for the patient. But there's one that we never question, and that's the AI tool, especially now that we have AI tools that are making calls for us. That AI tool that made the call, at what point are we going to be able to also question its sensitivity, specificity? Rather than saying, oh, the AI tool called it a prostate cancer, it must be right. I know influenced my decision. I moved on to that. Why don't we question that as well? And the only way we can do that is if we have a much bigger audience of AI-enabled practitioners. And that doesn't mean we need coders. We just need people who understand not only the capabilities, but just as importantly, the limitations of these things. So that's why I think education by far is the most important thing we as a community need to do. And especially since we manage a lot of the test developments and diagnostic entities as a profession.
Oh, that's a great point. Thank you, Dr. Rashidi, because we all are more and more using, LLM, especially things like ChatGPT or others in our day-to-day practice. And being in medicine, we have to be really careful, as you mentioned, that you have to have the human factor all the time and not get biased, because hallucination for a movie recommendation is fine, but you cannot allow that to for patient care. So that, I think, is a very great point that you mentioned. With that in mind, there is one question that came up from one of our viewers, is that what about the practical utility of LLMs beyond the hype? If you have to say, because nowadays, we have viewers from all over the world, but with ChatGPT or any other LLMs which are easily available without subscription. So if you want to suggest that, okay, these are some 5 regular uses in pathology practice that you can use, these LLMs. So do you have anything to suggest to our viewers?
Yeah, I do. I'll tell you, I'm not supposed to show it, but I can tell you that we have a framework. I'm not going to tell you the name of it. It's coming out soon, but it's been used in clinical service. I've used it actually in sign-outs for the past year. It's approved by our UPMC AI governance for usage for our quality, QA studies for so far that we've been using it. And it uses LLM, but it's not just LLM. It uses LLM and other types of technology tools combined, where it's enabling I'm on HemePath, and as you've seen those bone marrow reports, they're very large. You have to write comments that are very specific. So using technology tools and LLMs mixed in, we have a framework that now, instead of, taking 30 minutes to do write-up and review of my typical bone marrow, I can do the entire thing now in 5 minutes. And that's because mostly I'm spending time reading it. And so the LLM and the tech tools that we have incorporated can then do the whole write-up for me as what I put in input. But then on top of that, the advantages that they bring to the table is speed, so that I can get the diagnosis out much faster. That's one. So then the whole work-life balance becomes kind of an improvement. But besides that, from a patient care safety issue, standardization of the notes. Now all my notes are basically the same standard way. And clinicians know exactly where to look for what within my report. And then the most important is, when we have long reports, when I put something on page 1, let's say accidentally I set 37% blasts, and the thing may pop up a thing for me and say, are you sure this doesn't match your micro findings on page 3? Where my transcriptionist would not be able to tell me that. I know a Dragon doesn't tell me this. My own templates that I basically fill in will not do this. So using these that help us drive quality reassurance as well is just as important as we go into it. But we're doing it in baby steps. So we're not going full in and saying, here's the LLM, let it write everything up for us. What we're doing is we use our own traditional ways of technology-based filling, and then LLM helps with the comments section. And then I concentrate on the comments, seeing if the stuff that it filled in is accurate, but then the other parts are auto-populated much, much faster. And then hopefully in the future, I'll show you a version of it after, Pitt has, put the IP stuff through.
Right, I think that's a great point. Not to use it to generate the report, but
Yeah,
use it to refine the report. And then,
exactly.
as you said, that HIMPAT is one of those fields where the reports can be long and then the comments can be long. So then, sometimes on a busy day, so things can get, there can be misspelling and things like that. So those, I think, can be easily taken care of just by putting the report that we have generated into an LLM, which is modifying our, languages and things like that. I think that is very useful for anybody, across the world, whoever is practicing. It can, as Dr. Rashidi is saying, that it can, help you in reducing your time, and then also it would be more correct. At least it is checking the grammar already for you, right?
100%.
Thank you. I think these are all the questions, and there are a lot more. Maybe you all can reach out to Dr. Rashidi. His email is there, and he's also on social media. You can reach out. And as Dr. Rashidi has mentioned, that there is a 7-part article that there are 7 articles on pathology, modern pathology. So you must definitely read those articles. And if you want to know more about all the details about the uses of AI in pathology, especially. And thank you so much for your
Do
insight
you
on.
mind, just so that the audience has that, do you mind taking that last, I'll copy that into the chat. If you can take those 7 articles and put it on your social media.
Yeah, I have already put the one
Oh, you
link
did.
to YouTube channel, so I will do it
Perfect.
on Facebook as well. Yeah, absolutely. And then many of them are open access, right? And they can
They're, they're
download and read.
all they're all
All
open
of them are
access.
open access, so
They're
you
all
just
open
have to find
access.
them on Modern Pathology and check the link on YouTube chat box. I already put it there, and definitely those are must read from Dr. Rashidi
So
and his
here's
team.
I'm adding in 2 more to those 8 or 7
Yep.
plus the preface. I put it in the in the
You
in
can add it in the Zoom chat box. I will copy paste it
oh,
out.
okay, great. I put it, it says I've gone over the word limit of the Zoom chat box. So I'll
Oh,
that's weird. So let me do it in uh here's that, and
okay, yeah.
I just put in, there they are. I
Yeah,
put it
so
as
all the 7, let me put them on
7, and here's 2 more in case people want to read about more statistics and also study design elements. These were ones that we had written for the Cleveland Clinic course. Um, and I'll put that in there too in case the audience wants that as well. So
Absolutely. And once you go to those links, so you will get access to all the articles there. And let me give the other ones, right? So this is the newer link that Dr. Rashidi is sharing. So please check on YouTube. And I haven't put it on the Facebook, but at least you can check on YouTube and find all of them. And again, like, thank you so much, Dr. Rashidi. This
thank
was.
you so much. Thanks for the audience for
Thank
being
you so
here.
much.
Thanks for the invite.
And you would be happy to hear that, Dr. Rashidi, we had viewers who joined from different parts of the world. And
Awesome.
I just was able to keep track of some of the viewers. Like they say that they joined from India, they joined from
That's awesome.
Cambodia, Mexico, Italy, Nigeria, to name a few. And thanks to all our viewers for your support to Pathcast, and hopefully you like all our lectures, and you can please follow us on different social media platforms. So we have on Facebook, YouTube, Instagram, as well as X, and we will continue our lecture series. And our next lecture is actually, we will have a conversation. We all over the world, we are very much using pathology outlines for our day-to-day. It has become our go-to knowledge source. But like, let's have a chat with Dr. Nat Parnick, who is a pathologist and who is the founder of Pathology Outlines. So he will be joining me on August 4th at same time. So we will hear from him about Pathology Outlines and what is his story about it and how he came up with it and how he is running it. And it's a great resource for all of us, no doubt. So hope to see you all, and then we will hear from Dr. Parnick. So thank you so much, all of you. Thank
Thank you.
you.
Thanks.
Thank you, Dr. Rashidi.
Thank you. So we're good, right?
Yes.
All right.
Yeah.
It was great seeing you. So thanks so much.